3I Atlas just pushed itself away from the Sun. This comet, the size of Manhattan hurtling through our solar system at 137,000 miles per hour, did something on October 29th that comets are not supposed to do. It accelerated, from some force we cannot fully explain. NASA's navigation engineers detected it 4 arcseconds off course, moving with 2 separate acceleration vectors, one pushing radially away from our star, another sideways across its path. The numbers demand an explanation that breaks what we know about ice and rock. Either this interstellar visitor just lost a sixth of its total mass in explosive outgassing, unlike anything we have seen before, or something else is happening out there in the darkness beyond Mars. October 29th. 3I Atlas reaches perihelion, its closest approach to the Sun, at a distance of 203 million kilometers. Astronomers around the world train their instruments on this spot, waiting to see what happens when an interstellar visitor gets blasted by solar radiation more intense than anything it has encountered in millions of years of drifting through the frozen darkness between stars. The data streams in from the Atacama Large Millimeter Array in Chile, from NASA's Punch satellite, from observatories scattered across 6 continents. And then someone notices the numbers are wrong. Davide Farnocchia sits at his desk at NASA's Jet Propulsion Laboratory in Pasadena. He is a navigation engineer, the kind of person who tracks objects moving through space with mathematical precision. His job involves calculating trajectories, predicting where things will be based on the iron laws of gravity and momentum. He has been watching 3I Atlas for months, refining the orbital parameters, building a model of its path through our solar system. The model tells him exactly where the comet should be, on this date, at this hour, down to fractions of an arcsecond. 3A Atlas is not there. It is 4 arcseconds away in right ascension from where pure gravity says it should be. 4 arcseconds might sound small. In astronomical terms, it represents millions of kilometers of deviation from a calculated path. This is not measurement error. This is not noise in the data. Every object in space moves according to gravity. The sun pulls. The planets pull. These forces are predictable, calculable, understood down to the tiniest decimal point. When something moves differently than gravity predicts, we call it non-gravitational acceleration. And for a comet, there is usually one explanation: outgassing. Ice turns to vapor when heated by the sun. Jets of gas shoot out from the surface, and the whole object gets pushed like a balloon releasing air. We see this all the time with comets from our own solar system. But 3I Atlas is not from our solar system. It came from somewhere else, carrying ice and rock formed in orbit around a star we cannot identify, potentially billions of years ago. And now, as it swings past our sun, it is accelerating in ways that demand an explanation. The data shows 2 separate components of force. One pushes radially away from the sun at 135 kilometers per day squared. Another pushes transversely, sideways relative to the sun's direction, at 60 kilometers per day squared. Think about that structure for a moment. 2 distinct acceleration vectors, both measurable, both confirmed, not random, not chaotic. Structured force applied to an object that should be following a ballistic trajectory through empty space. And that is just the beginning of what makes October 29th strange. Let me walk you through what those acceleration numbers actually mean for 3I Atlas. When Avi Loeb, a theoretical physicist at Harvard, sees Farnocchia's report, he immediately starts calculating. The math here is straightforward physics, the kind you could work out on paper if you remembered your college mechanics. It is called the rocket equation, and it tells you how much mass an object must lose to accelerate itself by a given amount. The non-gravitational force equals mass times acceleration. Standard physics. But when that force comes from ejecting material, like gas streaming off a comet's surface, you have to account for momentum conservation. The force equals the rate of mass loss multiplied by the ejection velocity of that mass. Loeb plugs in the numbers. He assumes the gas is shooting off the surface at a few hundred meters per second, typical for sublimating ice heated by the sun. The calculation spits out a result that makes him stop and recalculate. To produce the observed acceleration, 3EI Atlas would need to be losing mass at a rate that would consume half of its total bulk in just 6 months. Half of its mass. Over the 1-month period when it crosses through the perihelion region, the comet would shed approximately 10% of everything it is made of. We are not talking about a gentle dusting of ice crystals here. We are talking about explosive, catastrophic evaporation that would tear the object apart in geologically rapid time. Scientists have measured the mass loss rate from 3I Atlas using the James Webb Space Telescope earlier in its approach. The telescope detected about 150 kilograms per second evaporating from the surface in August. That number produced no detectable non-gravitational acceleration back then, which led researchers to conclude that 3E Atlas must be extremely massive, at least 33 billion tons, with a solid nucleus over 5 kilometers across. But now, in late October, to get the acceleration Farnocchia measured, you would need to multiply that mass loss rate by orders of magnitude. You would need a gas cloud around 3I Atlas so dense, so voluminous, that it should be blindingly obvious to any telescope pointed in its direction. Here is the test, then. The acid test that will tell us what is actually happening. If this acceleration comes from natural cometary outgassing, if 3I Atlas is just a really active comet doing comet things, then we should see an absolutely massive plume of gas surrounding it when it emerges from behind the sun in November and December. Not a faint haze, not a subtle coma, a dense, unmistakable cloud carrying at least 5.5 billion tons of ejected material. The European Space Agency's JUICE spacecraft will be the first to look in the first week of November. Then, on December 19th, 3I Atlas will make its closest approach to Earth at a distance of 269 million kilometers. Every major ground-based telescope will be watching. Hubble will be watching. Webb will be watching. Hundreds of amateur astronomers will train their equipment on that spot in the sky. And if we do not see that massive gas cloud, then the rocket equation tells us something extraordinary. It tells us that the acceleration we measured cannot be explained by evaporating ice, which means we need a different explanation for why an interstellar object just pushed itself off course while passing through our solar system. What that explanation might be is something we will come back to. But first, you need to understand just how strange the structure of this acceleration actually is. Most comets that show non-gravitational acceleration display it in one direction, radially outward from the sunday. The physics makes sense. Surface heats up, ice sublimates, gas jets push directly away from the heat source. It is like a bottle rocket pointed straight up. Simple, predictable. The signature of sublimation-driven thrust. 3 Atlas has two vectors, two separate, measurable components of force acting on it simultaneously at perihelion. The first pushes radially away from the sun, which fits the expected pattern, but the second one pushes transversely, perpendicular to the sun-comet line, at 60 kilometers per day squared. That transverse component requires explanation. For natural outgassing to produce transverse acceleration, the jets of gas would need to be coming off the surface at an angle, not perpendicular to it. This happens when a comet is rotating and the sublimation happens preferentially from certain areas exposed to sunlight while others remain in shadow. The rotation carries the active areas around the nucleus, and the net effect of all those angled jets can produce a sideways push. We see this on short-period comets in our own solar system all the time. But 3I Atlas is not supposed to be rotating quickly. Early observations of the object showed minimal light curve variation, less than 0.2 of a magnitude over a 29-hour span. That suggests either very slow rotation or a relatively round shape that does not change much in brightness as it turns. Neither of those characteristics typically produces strong transverse acceleration. So, we have structured two-component thrust acting on an object that displays weak rotational signatures. The vectors point in specific directions with measurable magnitudes. Over the course of approximately 1 month, this acceleration would shift 3I Atlas from its purely gravitational path by a distance equal to about 10 times Earth's radius. Not enough to dramatically change where it is going. Not enough to send it crashing into anything or veering off into a completely different trajectory. Just enough to be measurable. Just enough to require explanation. Think about what you would see if you were watching this happen in real time. An object the size of a city block, moving at speeds that would cross the distance from Los Angeles to New York in about 2 minutes, suddenly experiencing forces that push it both away from the sun and sideways across its orbital plane. Forces that operate while the object is hidden behind the sun's glare, during the brief window when direct observation from Earth becomes nearly impossible. The timing raises questions. So does the location. Perihelion is exactly where you would expect maximum cometary activity if this is natural. It is also exactly where you would perform something called a reverse Oberth maneuver if you wanted to use the sun's gravity to brake an incoming spacecraft. The Oberth effect lets you gain or lose orbital energy most efficiently when you are moving fastest, which happens at perihelion. If something wanted to slow down and stay in the solar system rather than escape back into interstellar space, passing close to the sun and then applying thrust would be the mathematically optimal approach. But we are getting ahead of ourselves. Before we go down that particular road, we need to look at what happened to 3I Atlas during those hours when it sat behind the sun, eclipsed from Earth's view. Because the acceleration was not the only anomaly detected at perihelion. Comets are supposed to be red, or at least reddish. The dust particles surrounding a comet scatter sunlight, and that scattering process tends to make the reflected light appear warmer in color than the sun itself. Think of a sunset, where Earth's atmosphere scatters blue light away and lets red light through. Cometary dust does something similar, absorbing shorter wavelengths and reflecting longer ones. Plus, the surface of the comet nucleus is typically cold, much colder than the sun's photosphere, which means any light it emits thermally would be in the infrared, below the red end of the visible spectrum. 3I Atlas turned blue. Multiple spacecraft instruments captured images of the object at perihelion. The Stereo satellite, the SOHO observatory, the GOES-19 weather satellite, all saw the same thing as 3I Atlas passed its closest point to the Sunday. Instead of appearing reddish, like every model of cometary dust would predict, the object displayed a distinctly blue coloration, bluer than the sun itself. This is anomaly number 9 on the growing list of unexpected properties that 3I Atlas has displayed since its discovery in July. Avi Loeb catalogues these anomalies systematically, publishing them as each one emerges from new observations. The blue color might have a natural explanation involving ionized carbon monoxide in the coma, which can emit blue-shifted light under certain conditions. But for that to work, you would need very specific chemistry and very specific excitation conditions, neither of which has been confirmed from spectroscopic observations. The alternative explanation is that we are seeing thermal emission from something hot, hotter than the expected surface temperature of a comet, at 1.4 astronomical units from the Sunday. Hot enough to emit visible blue light, which would require temperatures in the thousands of degrees. An engine, for instance, would be hot. A propulsion system generating thrust would produce waste heat that might glow blue. But let me be clear about what we are and are not saying here. The blue color is strange. It does not fit simple models. It adds to a pattern of observations that keep defying our expectations about how a comet from interstellar space should behave. It is not, by itself, proof of anything except that 3I Atlas refuses to act like the objects we are familiar with. What makes the color shift particularly intriguing is the timing. The blue appearance coincides exactly with the period of non-gravitational acceleration. Both happen at perihelion. Both emerge from data collected during the narrow window when 3I Atlas was behind the sun from Earth's perspective, observable only by spacecraft positioned differently in the solar system. And both disappear or diminish once the object moves past perihelion and begins its outbound journey. The correlation between color change and acceleration might be coincidence. Two separate, unrelated phenomena that just happen to occur simultaneously during the moment of maximum solar heating. Or they might be linked, different manifestations of the same underlying process, whatever that process turns out to be. December 19th will tell us more. That is when 3i Atlas makes its closest approach to Earth and becomes optimally positioned for observation by every major telescope humanity has built. Spectroscopy can reveal the chemical composition of the coma, if there is one. Photometry can measure brightness variations and color accurately. Radar might even be able to image the surface if the object is reflective enough and the geometry works out. But before we get to what happens in December, we need to talk about how 3i Atlas compares to the other interstellar object that showed non-gravitational acceleration. Because this story has happened before, and the parallels are unsettling. October 19th, 2017. Astronomers discover the first confirmed interstellar object passing through our solar system. They name it Oumuamua, Hawaiian for scout or messenger. The object is small, maybe 400 meters long and 40 meters wide, tumbling end over end as it races past Earth at 87 kilometers per second. And it does something comets are not supposed to do. It accelerates. The deviation from a purely gravitational trajectory shows up clearly in tracking data as Oumuamua moves away from the Sunday. The acceleration is small but measurable, persistent over weeks of observation. Scientists immediately suspect outgassing, the standard explanation for cometary non-gravitational forces. They point telescopes at Oumuamua, looking for the characteristic signature of sublimating ice, a bright coma of gas and dust, a tail extending away from the nucleus, spectral lines indicating water vapor or carbon dioxide or other volatiles. They find nothing, no coma, no tail, not even when NASA's Spitzer Space Telescope conducts deep observations specifically designed to detect faint outgassing that other instruments might have missed. Oumuamua accelerates without any visible evidence of the mechanism that should be producing that acceleration. The object becomes what comet experts start calling a dark comet, something that displays comet-like non-gravitational forces but no comet-like appearance. The controversy that follows dominates astronomy discussions for years. Some scientists propose exotic explanations, a chunk of solid hydrogen ice that would sublimate without leaving visible traces, or an extremely low-density object made of fractal dust aggregates. Others suggest Oumuamua might be artificial, a light sail or probe from another civilization. That hypothesis, championed by Avi Loeb and mathematician Shmuel Bialy in a technical paper, generates intense debate. Most astronomers favor natural explanations, but the object disappears from view before anyone can gather enough data to settle the question definitively. Now, 8 years later, 3i Atlas is repeating the pattern: non-gravitational acceleration at perihelion, observations that do not quite match what we expect from a normal comet. A size and trajectory that raise questions about formation and origin. The parallels are difficult to ignore, but there are differences too. Oumuamua was small and elongated, possibly shaped like a cigar or a pancake, depending on which interpretation of the light curve data you believe. 3i Atlas is massive, potentially 5 to 20 kilometers across, with a more typical comet-like shape. Oumuamua showed no visible coma at all. 3i Atlas definitely has cometary activity, confirmed by multiple telescopes observing a diffuse cloud of dust and gas around the nucleus, though that activity has been peculiar in its own ways. The biggest difference might be the timing of observation. Oumuamua was discovered after it had already passed perihelion and was heading outbound. By the time we knew it was interstellar, we had limited time to study it before it faded from view. 3i Atlas was discovered early, in July, giving astronomers months of observation time before perihelion. And unlike Oumuamua, 3i Atlas will remain visible for months after perihelion, bright enough for detailed study as it heads back out into interstellar space. Which means we have a second chance, a chance to do the observations we could not do with Oumuamua, a chance to catch definitive proof of massive outgassing if that is what is producing the acceleration, or a chance to confirm that we are seeing something else, something that does not fit into our current understanding of how icy bodies from other star systems should behave when they pass through ours. Darrell Seligman, a physicist at Michigan State University who studies these objects, reminds us that cometary non-gravitational acceleration is actually quite common. Comets do this all the time. They blow gas off their surfaces. They act like natural rockets. They deviate from purely gravitational paths. It would be strange, Seligman points out, to see a comet without any non-gravitational acceleration at all. The fact that 3I Atlas shows this behavior is not necessarily anomalous. What is anomalous is the context, the size, the timing, the pattern of observations that keep revealing unexpected properties, and most of all, the mass. Let me show you a calculation that breaks our models of interstellar space. Scientists estimate the number density of interstellar objects drifting through the galaxy based on observations and theory. We know roughly how much solid material gets ejected from planetary systems during their formation. We know how that material should be distributed across the volume of interstellar space. From those numbers, we can predict how often objects of different sizes should pass through our solar system. Small objects, like Oumuamua, should be common. Objects the size of 3I Atlas should be incredibly rare. Statistically, we should detect approximately 100,000 Oumuamua-sized objects before we ever see something as massive as 3I Atlas. 100,000. That is the ratio predicted by the standard model of how planetary debris is distributed by size. We have detected exactly 3 interstellar objects total: Oumuamua in 2017, Comet Borisov in 2019, and now 3I Atlas in 2025. 3 objects, and one of them is orders of magnitude more massive than probability says it should be this early in our observation campaigns. The numbers do not add up. Either we have been phenomenally lucky, catching one of the rarest possible interstellar visitors in our 3rd detection ever, or something is wrong with our understanding of the interstellar object population. Maybe large objects are more common than theory predicts. Maybe the distribution of sizes follows a different power law than we assumed. Maybe the source regions that produce these wanderers generate more big chunks than our models account for. Or maybe 3I Atlas is not a random sample from the interstellar object population. Maybe it is unusual for reasons that have nothing to do with natural planetary system debris. The mass itself creates headaches for any explanation. Based on the lack of detectable non-gravitational acceleration during the months before October, researchers calculated that 3I Atlas must have a mass of at least 33 billion tons. The nucleus is probably more than 5 kilometers across, possibly as large as 20 kilometers depending on assumptions about density and shape. That makes it 3 to 5 orders of magnitude more massive than Oumuamua and larger than Borisov as well. Think about what that means for the outgassing scenario. A 5-kilometer chunk of ice and rock heated by the sun should produce observable mass loss. We did observe some, about 150 kilograms per second in August when the Webb telescope looked at it, but that rate was too low to produce any measurable thrust. The object was too massive, too inert, to be pushed around by that level of sublimation. Now, suddenly, in late October, it is accelerating. The only way to reconcile those observations is to propose that outgassing increased dramatically, maybe by factors of hundreds or thousands, right at perihelion. Not impossible. Perihelion is where solar heating is most intense. New areas of fresh ice might have been exposed. Different volatile compounds with lower sublimation temperatures might have become active. Comets from our own solar system sometimes have outburst events where activity spikes suddenly, but the required mass loss is still extraordinary. 10% of the total object in 1 month. A cloud of gas weighing billions of tons. And remember, we did not see evidence of this before perihelion, when telescopes were watching carefully. The Hubble Space Telescope imaged 3I Atlas on July 21st, revealing a teardrop-shaped cocoon of dust, but nothing suggesting imminent catastrophic mass loss. The Webb telescope observations in August showed modest but not extreme activity. The acceleration appears suddenly, right when direct observation becomes difficult, right when 3I Atlas is positioned behind the Sunday. That might be coincidental timing. Solar heating is strongest at perihelion after all, but it means we have to wait for the object to emerge in November and December to see if the predicted gas cloud actually exists. Which brings us to the question everyone wants to ask, but few scientists will address directly in published papers. What if we do not see the gas cloud? What if December comes, and 3I Atlas looks essentially the same as it did before, without evidence of losing billions of tons of material? What then? Scientific papers use careful language. They present hypotheses, data, analysis, interpretations. They acknowledge uncertainty. They avoid making claims that go beyond what the evidence strictly supports. So, when Avi Loeb publishes a note saying that the non-gravitational acceleration might be the technological signature of an internal engine, he is doing something unusual. He is putting into peer-reviewed literature an idea that most of his colleagues consider deeply unlikely. Not impossible, just deeply unlikely. Let me walk through the logic here without prejudging the conclusion. We have an object from interstellar space showing structured acceleration that cannot be easily explained by observations so far. If natural outgassing is the explanation, we should see specific signatures in upcoming observations. A massive gas cloud, spectral evidence of sublimating volatiles, possibly fragmentation if the mass loss is as extreme as calculations suggest. These are testable predictions. December will either confirm or refute them. If those signatures are not present, if 3I Atlas somehow accelerated without losing detectable amounts of mass, then we need an alternative mechanism. The physics are straightforward. Acceleration requires force. Force requires momentum transfer. Momentum transfer requires ejecting something or pushing against something. In space, with no surrounding medium to push against, the only option is to eject mass. Unless you are doing something exotic like generating thrust from electromagnetic fields or manipulating gravity itself, neither of which we know how to do, an internal engine capable of producing the observed acceleration would need to work like a rocket, expelling propellant to generate thrust. The fuel would be carried internally rather than existing as surface ice. The exhaust might be hot enough to glow blue. The operation might be timed to occur at perihelion for reasons related to thermal management or energy harvesting or trajectory optimization. This sounds like science fiction. It is supposed to sound like science fiction, but Loeb's point is that we should let the data guide us rather than ruling out possibilities in advance based on what we think is likely. If the natural explanation fails to match observations, we need to consider what remains, however improbable it might seem. The history of astronomy includes multiple examples of phenomena that were initially dismissed as impossible and later confirmed. Pulsars were briefly thought to be artificial beacons before we understood that they are rotating neutron stars. Fast radio bursts generated speculation about extraterrestrial signals before we found natural sources. The universe repeatedly does things we did not expect, using mechanisms we did not anticipate. But the history of astronomy also includes countless examples of anomalies that turned out to have perfectly mundane explanations once we got better data. Weather balloons mistaken for UFOs. Instrument glitches misinterpreted as new physics. The default assumption should always favor natural explanations until the evidence overwhelmingly points elsewhere. So, where does that leave us with 3I Atlas? In a state of principled uncertainty, we have observations that do not quite fit our models. We have predictions about what we should see next if various explanations are correct. We have the intellectual honesty to acknowledge that we do not know everything about how ice and rock behave when exposed to solar radiation after millions of years in interstellar cold. What we do not have yet is definitive proof of anything. The gas cloud observations in December will help. so will continued tracking of the object's trajectory as it leaves the inner solar system. So will analysis of the spectroscopic data that multiple telescopes will collect over the coming months. Science is a process, not a destination. We accumulate evidence, test hypotheses, refine our understanding, but the question hangs there, unavoidable. What if this object is not natural? What would that mean for humanity? Before we spiral too far into speculation, let me bring us back to something concrete, where 3E Atlas came from and where it is going. The trajectory tells a story, if you know how to read it. 3 Atlas entered our solar system from the direction of the constellation Ophiuchus, moving at about 60 kilometers per second relative to the Sunday. That is its velocity at infinity, the speed it would have if gravity had no influence, the speed it carried from interstellar space. As it fell inward toward the Sun, gravity accelerated it, increasing its velocity to peak at around 68 kilometers per second at perihelion. The orbit is hyperbolic, with an eccentricity of 6.137. Any eccentricity above 1 means the object is not gravitationally bound to the Sun, that it came from elsewhere and will return to elsewhere after its brief visit. The eccentricity of 3I Atlas is high even by interstellar object standards, indicating very loose interaction with our star's gravity well. But here is what makes the trajectory unusual. The orbital plane of 3I Atlas is tilted only about 5 degrees from the ecliptic, the plane in which Earth and the other planets orbit, and the motion is retrograde, meaning the comet moves opposite to the direction planets orbit. Most objects entering from random directions in interstellar space would have much higher inclinations, coming in at steep angles to the ecliptic plane. A low inclination retrograde orbit is not impossible, but it is statistically uncommon. That geometry has implications. If you wanted to observe or interact with multiple planets in a solar system efficiently, approaching along the ecliptic plane gives you access to the most targets with the least need for plane changes, which are expensive in terms of delta V. 3 Atlas will pass relatively close to Venus on November 3rd, having already passed Mars on October 3rd at a distance of about 28 million kilometers. Later, in March of 2026, it will approach Jupiter to within about 50 million kilometers before finally exiting the solar system for good. A series of planetary flybys, a trajectory that threads through the most interesting parts of the solar system, an orbital plane aligned with where the action is. Again, this could all be coincidence. Random chance occasionally produces unlikely configurations, but it adds to the overall pattern of observations that keep making you tilt your head and go, The timing of the acceleration also fits a specific maneuver called a reverse O-berth. If you wanted to slow down an interstellar probe and capture it into orbit around a star, the most efficient place to apply thrust would be at perihelion when you are moving fastest. The O-berth effect means that propellant spent at high velocity produces more change in orbital energy than the same propellant spent at low velocity. It is counterintuitive but mathematically rigorous. 3 Atlas reached perihelion behind the Sun from Earth's perspective. The Sun's corona is a natural shield, blocking radio communications and most optical observations. If you wanted to perform a maneuver with minimal observation, that would be an ideal location. Eclipse yourself with the star you are trying to capture into orbit around, apply thrust in the shadow, emerge on a modified trajectory. Am I saying this is what happened? No. I am saying the geometry and timing are consistent with this scenario, which makes it worth examining. Most scientists think 3I Atlas is simply an interstellar comet doing comet things in an environment somewhat different from where it formed. The anomalies will probably resolve into natural explanations once we have better data. Probably. What bothers some researchers is the accumulation of small anomalies. Individually, each one can be explained away or rationalized as within the range of possibility for natural objects. But together, they form a pattern that resists easy categorization: the low inclination, the retrograde orbit, the extreme mass, the insufficient outgassing before perihelion, the sudden acceleration during perihelion, the blue color, the structured two-component thrust, the statistical improbability of finding such a large object so early. At what point does a collection of anomalies stop being individual quirks and start being a signature of something genuinely different? That is a question without a clear answer. Science proceeds by testing specific hypotheses, not by gesturing at vibes. We need the December observations. We need hard data about that gas cloud. But until then, the trajectory of 3I Atlas remains one more thing that makes us wonder. Let me tell you about what happened during the weeks when 3E Atlas was closest to the Sunday. From late October through most of November, the comet sat behind our star from Earth's perspective. Solar conjunction, astronomers call it, when an object's apparent position in the sky is too close to the Sun to observe safely with most instruments. The Sun is bright. It overwhelms nearby objects. Telescopes cannot look directly at it without specialized filters or coronagraphs. This is not a conspiracy. This is geometry. Earth orbits the Sunday. Other objects orbit or pass by the Sunday. Sometimes the three bodies line up in ways that make observation difficult or impossible from our vantage point. It happens with planets, asteroids, comets, spacecraft, anything in the solar system. We lose visual contact during conjunction periods and have to wait for the geometry to change. But not all vantage points are on Earth. NASA operates multiple spacecraft positioned around the inner solar system specifically to observe the Sun and its immediate surroundings. The Solar and Heliospheric Observatory, SOHO, sits at the L1 Lagrange point between Earth and the Sunday. The Solar Terrestrial Relations Observatory, STEREO, includes satellites with different viewing angles. The Punch mission uses a constellation of satellites to image the Sun's outer corona. These spacecraft caught glimpses of 3I Atlas during perihelion passage. So did the GOES-19 weather satellite, which has solar monitoring instruments. So did the Parker Solar Probe, though from a different position in its highly elliptical orbit. The European Space Agency's solar orbiter had opportunities for observation, and the Mars Reconnaissance Orbiter, equipped with the high-rise camera capable of extraordinary resolution, happened to be positioned well for imaging 3I Atlas when it passed relatively close to Mars in early October. Those observations exist. Some of them have been made public. The high-rise images, if they captured usable data, remain unreleased as of early November. Avi Loeb has specifically requested that NASA make those images available to the scientific community, arguing that high-resolution surface imagery could answer key questions about the object's composition and structure. What did the spacecraft that could observe during perihelion actually see? We know they detected the blue color shift. We know they captured the brightening of the object, which increased dramatically as it approached the Sun, scaling inversely with distance raised to the -7.5 power. That is an unusually steep brightness curve, steeper than most comets display, suggesting either changing surface properties or increasing activity rates beyond what simple heating models predict. The spacecraft that measured the non-gravitational acceleration, the data source for Farnotch's report, was likely ALMA, the Atacama Large Millimeter Array, based on Loeb's description of how the deviation was detected. ALMA is a ground-based telescope array in Chile, but it can observe objects near the Sun by looking at wavelengths where solar glare is less overwhelming. The 4 arcsecond deviation in right ascension, compared to the predicted position, provided the first clear evidence that 3I Atlas was not following a purely gravitational path. Now the comet is emerging from behind the Sunday. As November progresses, it becomes observable again from Earth, though still relatively faint and close to the horizon at certain latitudes. The geometry improves through December. By December 19th, when 3I Atlas reaches its closest point to Earth, at 1.8 astronomical units away, essentially every telescope that can point in that direction will be trained on it. That is when we get our answer about the gas cloud. If 3I Atlas lost 5.5 billion tons of material at perihelion, producing the rocket effect that generated the measured acceleration, we will see it. Spectroscopy will show the composition, revealing whether it is water vapor or carbon monoxide or some other volatile compound. Photometry will measure the density and extent of the cloud. Radar might even bounce signals off condensed particles if any are present. The International Asteroid Warning Network has organized a coordinated observation campaign running from late November through late January. Multiple observatories worldwide will contribute data, creating a comprehensive picture of the object's physical state after perihelion passage. This is not a casual study. This is a full-court press to characterize 3I Atlas as thoroughly as possible before it moves too far away and becomes too faint for detailed investigation. What we learn in December will either close the book on this mystery or blow it wide open. Megan Schwamb studies planetary science at Queen's University Belfast in Northern Ireland. When asked about the non-gravitational acceleration of 3I Atlas, she emphasizes the conventional interpretation. Comets experience changes in the rate of volatile ice sublimation as they approach the sunday. Increased sublimation means increased outgassing. Increased outgassing produces measurable acceleration. We see this effect in long-period and short-period comets all the time. The peer-reviewed literature on 3I Atlas, accumulated over the months since discovery, shows substantial evidence of cometary activity and evolving surface composition. This is the mainstream position. 3 Atlas is an interstellar comet, genuinely exciting because interstellar comets are rare, but fundamentally similar to comets we already understand. The anomalies are edge cases, the result of observing a type of object we have limited experience with, under conditions we have never precisely measured before. As we gather more data, the anomalies will resolve into natural explanations consistent with known physics. Darrell Seligman at Michigan State echoes this view. Cometary non-gravitational acceleration is not just common, it is nearly universal. You would be more surprised to find a comet that showed no acceleration at all. The rocket effect from outgassing has been measured on hundreds of comets. The fact that 3I Atlas displays this behavior is actually evidence that it is behaving like a normal comet, not evidence of anything exotic. Seligman goes further, pointing out that we have identified a category of objects called dark comets in the near-Earth environment. These are objects that show comet-like non-gravitational accelerations but no visible coma or tail. Oumuamua fits this category. The existence of dark comets as a natural phenomenon means that non-gravitational acceleration without obvious outgassing is not unprecedented. It is weird, but weird in a way that natural processes can apparently produce. The skepticism toward exotic explanations is grounded in good scientific practice. Extraordinary claims require extraordinary evidence. The claim that 3 Atlas might be artificial is about as extraordinary as claims get. The burden of proof is high, rightly so. Before we conclude that we are looking at alien technology, we need to exhaust every possible natural explanation and find them all wanting. Has that happened yet? No. The natural explanation still has room to work. The December observations might show exactly what the outgassing hypothesis predicts. The massive gas cloud might appear right on schedule. The spectroscopy might reveal chemical signatures entirely consistent with a comet from another star system vaporizing ices that formed billions of years ago in a different stellar environment. But there is a tension in the scientific community that is worth acknowledging. Some researchers are comfortable entertaining the possibility of artificial objects, even while considering it unlikely. Others find the whole discussion unproductive, a distraction from the real work of characterizing what is almost certainly a natural phenomenon. The split is not about the data, which everyone agrees on. It is about what range of hypotheses we should seriously consider when the data does not quite fit our models. Avi Loeb argues that scientific truth is not decided by authority or popularity, but by attention to data. If the data eventually shows that 3I Atlas cannot be explained by natural cometary outgassing, then we need to consider alternatives, regardless of how uncomfortable they make us. Ruling out explanations a priori, before looking at the evidence, is precisely what science is supposed to avoid. His critics argue that assigning non-zero probability to the artificial hypothesis before exhausting natural alternatives is premature. It generates media attention and public speculation that gets ahead of what the science actually supports. It risks crying wolf, spending credibility on unlikely scenarios that will probably resolve into mundane explanations. Both positions have merit. The disagreement is about process and threshold, not about reality. Reality does not care what we think is likely or what makes us comfortable. Reality is what it is. The December observations will bring us closer to understanding what reality actually contains. Meanwhile, we wait. The comet moves through space according to laws that do not change based on our uncertainty. In 2 weeks, we will know more. In a month, we will know much more. By early 2026, this will either be a fascinating footnote about an unusual but natural comet, or it will be something that changes everything. December 19th, 2025. Mark the date. 3I Atlas reaches its closest approach to Earth at 269 million kilometers. Close in astronomical terms means utterly distant by human scales. Light takes about 15 minutes to cover that gap, but for telescopes, it is near enough for detailed observation. The test has specific, measurable criteria. If the non-gravitational acceleration detected at perihelion resulted from natural cometary outgassing, 3I Atlas must have expelled approximately 6 billion tons of material. That material forms a cloud of gas, mostly simple molecules like water vapor, carbon dioxide, carbon monoxide, possibly methane or ammonia, or other volatiles depending on composition. The cloud expands outward from the nucleus at speeds of hundreds of meters per second, gradually dispersing but remaining dense enough to scatter light and produce spectral signatures. Telescopes will look for this cloud using multiple techniques. Direct imaging will reveal the spatial extent and brightness. Spectroscopy will identify the molecular species present and measure their abundance. Radio observations can detect certain molecules through their characteristic emission lines. Infrared observations can measure thermal emission from dust particles mixed with the gas. If we see what the models predict, case closed. 3I Atlas is an interstellar comet that experienced an outburst event at perihelion, nothing more exotic than that. The anomalies were red herrings or measurement artifacts or edge cases of natural processes we do not fully understand yet. Science moves on to characterizing the object's origin, figuring out what stellar system it came from, using its composition to understand planet formation conditions in other parts of the galaxy. But if we do not see the predicted gas cloud, we have a problem. The acceleration happened, confirmed by multiple independent measurements of the object's position relative to where gravity says it should be. Acceleration requires force. Force requires momentum transfer. Where did the momentum come from, if not from expelled gas? The physics does not give us many options. Option 1. We missed the gas cloud somehow. Maybe it dissipated faster than models predicted. Maybe the composition was unusual in ways that made it hard to detect. Maybe our instruments were not sensitive enough or were pointed at the wrong wavelengths at the wrong times. This is possible, but would itself be anomalous. 6 billion tons of gas does not just vanish without a trace. Option 2. The mass loss happened but was much less than calculations indicated. Maybe the comet is even more massive than we estimated, massive enough that it could produce the observed acceleration with less relative mass loss. But we already pushed the mass estimate to extreme values to explain the lack of earlier acceleration. Going higher strains credibility. Option 3. The acceleration mechanism was not sublimating ice. Something else pushed 3I Atlas off course. This is where the conversation gets difficult, because in the vacuum of space, your options for thrust without visible propellant are limited. Electromagnetic effects? The solar wind carries momentum, but not enough to produce the measured acceleration at that distance. Radiation pressure? Again, too weak for an object this massive. Gravity anomalies? Those would show up in other ways and would not be limited to perihelion. That leaves propulsion, an internal system generating thrust by some means we cannot observe from outside. This sounds like science fiction, because it is science fiction in human experience. We have never built anything that could survive interstellar space for millions of years and still function. Our most distant spacecraft, Voyager, has been traveling for less than 50 years and is already experiencing system failures. The idea that something could traverse the gulfs between stars and retain active capabilities seems fantastical. But the universe is larger and older than human civilization. The galaxy has existed for over 13 billion years. Stars have been forming planets for nearly that entire span. Life on Earth emerged within a billion years of the planet's formation. Intelligence arose comparatively recently, but might not be unique. The statistical questions about how common technological civilizations are in the galaxy remain unsettled. We have no confirmed examples other than ourselves, but we also have not looked very thoroughly. If something artificial entered our solar system, we might recognize it, or we might not. Recognition depends on the object doing something that natural objects do not do. So far, 3I Atlas has done things that are unusual for natural objects, but not quite impossible for them. The measurements are strange, but not yet definitive. December gives us definition. Either we see the gas cloud or we do not. Either the natural explanation works or it does not. The data will not be ambiguous. Multiple independent observatories will confirm or refute the prediction. This is science operating as it should. Make a testable prediction, gather evidence, evaluate honestly. In 2 weeks we will know. And if the answer is that we do not see what we should see, if 3I Atlas remains enigmatic even under close scrutiny, then the questions we ask about this object will change in fundamental ways. Let me take you on a thought experiment. Suppose, for a moment, that 3I Atlas is artificial, not a comet, not a natural chunk of ice and rock, a probe, a vessel, something constructed by intelligence. What would that mean? First, it would mean we are not alone. That conclusion is massive, paradigm-shattering, the kind of thing that gets written in history books as a turning point in human self-understanding. We would have proof that other minds exist in the universe, minds capable of building things that cross the distances between stars. The Fermi paradox, the question of why we have not seen obvious signs of extraterrestrial civilizations despite the apparent likelihood that they should exist, would partially resolve. They exist. One of them sent something here. Second, it would mean that interstellar travel is possible in some form. Whether 3 Atlas represents a crewed vessel, an autonomous probe, or something else entirely, its mere existence would demonstrate that the engineering challenges of crossing light years can be solved. The energy requirements are staggering. Even at 60 kilometers per second, reaching the nearest star system would take tens of thousands of years. Faster transit requires more energy, possibly more than any chemical or nuclear propulsion system could provide. But possible does not mean easy, and absence of evidence is not evidence of absence. Third, it would raise the question of intent. Why is this object here? Is it exploring, gathering information, making observations? Is it performing scientific research, studying our solar system as a point of comparison to others? Is it looking for signs of life or intelligence? Did it detect our radio transmissions and come to investigate? Or is its presence purely coincidental, a random trajectory that happened to pass through our neighborhood during the brief window when humans were advanced enough to notice? The non-gravitational acceleration, if artificial, might have specific purposes, adjusting trajectory to target particular planets for close observation, performing orbital corrections to extend the visit time, preparing for capture into a bound orbit around the Sun or around one of the gas giants, testing propulsion systems after a long coast through interstellar space. Any of these could explain the measured forces. The timing at perihelion might relate to energy considerations. Stars are power sources. A probe might harvest solar energy to recharge systems or to provide thrust through photonic reflection or electromagnetic effects. The Sun's intense radiation field at 1.4 astronomical units is a resource, not just a hazard. An advanced system could potentially exploit that. But let me be absolutely clear. This is speculation piled on speculation, building castles from clouds. We have no evidence that 3I Atlas is artificial. We have anomalies that natural processes probably explain. Probably. The probability is high. Most astronomers would put it above 95%. Some would say 99%. The exotic interpretation remains a long-shot possibility, worth mentioning for completeness, but not worth betting on. Yet the human mind cannot help but wonder. We have been looking at the sky and asking if anyone else is out there for as long as we have been capable of asking questions. The search for extraterrestrial intelligence has been an organized scientific effort for over 60 years. We have listened for radio signals, looked for optical pulses, analyzed astronomical phenomena for signatures that would be hard to fake naturally. We have found nothing conclusive. Every candidate signal has either been explained as natural or remains too ambiguous to claim as definitive. If 3i Atlas turned out to be the first confirmed artifact of non-human technology, it would not arrive with a neat label and instruction manual. It would be strange, confusing, hard to interpret. The creators might be long dead. Their civilization collapsed billions of years ago, leaving only this silent messenger drifting through the void. Or they might still exist, watching our reaction, waiting to see what we do with the information. The implications would cascade through every field of human knowledge. Philosophy would grapple with our place in the cosmic hierarchy. Religion would interpret the discovery through existing frameworks or develop new ones. Politics would face questions about how to respond, whether to attempt communication, how to coordinate a global strategy if the object showed signs of interaction. Science would have an entirely new subject to study, potentially learning physical principles or engineering techniques that could take human civilization in unexpected directions. Or none of this will matter because 3i Atlas is just a comet and we are pattern-seeking creatures who see significance in randomness. December will clarify. Until then, we stand in the space between what we know and what we imagine, between evidence and inference, between the familiar universe and one that might be stranger than we ever anticipated. While we wait for December, let me tell you about something else strange that happened at perihelion. 3a Atlas got bright, much brighter than predictions indicated. Two researchers, Qicheng Zhang from Lowell Observatory and Carl Battams from the U.S. Naval Research Laboratory, analyzed observations from the stereo, SOHO, and GOES-19 instruments during September and October. They documented a rapid rise in brightness as the comet approached the sunday. The brightness scaled inversely with distance raised to the negative 7.5 power plus or minus 1. That is a steep curve, steeper than most comets display. Typical comets brighten roughly with the inverse square of distance, maybe inverse cube if they are particularly active. Inverse 7.5 is dramatic. It suggests that whatever makes 3i Atlas bright increases dramatically, almost explosively, as solar heating intensifies. Massive evaporation could explain this. If huge amounts of ice suddenly begin sublimating, the expanding gas cloud would scatter more sunlight, making the whole system appear brighter. The dust entrained in the gas would contribute to the scattering. The brightness surge would be a signature of the outburst that produced the non-gravitational acceleration. But here is the catch. The brightness surge produces visible evidence that should persist after perihelion. The cloud does not just instantly disappear. It expands, disperses, gradually becomes more tenuous, but remains observable for weeks or months. This is the same cloud we are looking for in December. If the brightness came from massive outgassing, we should see the remnants. The blue color observed at perihelion adds another layer. Bright usually means more scattered light, more particles in the way. Blue usually means something about the scattering mechanism or the light source is different from expectations. Dust scatters red light preferentially. Gas can emit at specific wavelengths depending on its composition and excitation state. Ionized carbon monoxide glows blue under certain conditions. So does hot metal. So does any thermal source above a few thousand degrees Kelvin. The combination of rapid brightening, blue color shift, and non-gravitational acceleration, all happening simultaneously during the perihelion passage, suggests these phenomena are related. They share a cause, whatever that cause might be. The simplest explanation is that 3I Atlas underwent a cometary outburst, a sudden increase in activity driven by solar heating, exposing fresh, volatile material. Comets sometimes crack, exposing new ice that sublimates rapidly. Comets sometimes spin up or down, changing which areas receive sunlight and altering outgassing patterns. But simple is not the same as proven. We need observations that confirm the mechanism. We need to see the aftermath and verify that it matches what the outburst hypothesis predicts. If 3I Atlas returns to its previous state without evidence of massive mass loss, if the brightness fades without leaving a detectable gas cloud, then the outburst explanation faces challenges. The alternative, once again, involves something generating light and thrust without the visible signatures we associate with sublimating ice. A propulsion system produces waste heat. If that heat is in the thousands of degrees, it glows blue. If the thrust is vectored carefully, it can accelerate the object without producing an obviously expanding cloud. These are engineering problems, solvable in principle if you have advanced enough technology. Am I suggesting this is what happened? I am suggesting we do not know yet. The data is consistent with multiple interpretations. Some interpretations are more likely than others based on what we know about natural processes and what we assume about technological capabilities. But likelihood is not certainty. We wait for evidence to narrow the possibilities. What we do know is that 3I Atlas drew attention from astronomers worldwide precisely because it kept doing unexpected things. The brightness surge is one more item on the list. The list keeps growing. At some point, the accumulation of unexpected observations demands a comprehensive explanation that ties everything together. December might provide that explanation, or December might deepen the mystery. The International Asteroid Warning Network begins its coordinated observation campaign on November 27th and continues through January 27th, 2026. This is a 2-month intensive effort involving observatories across the globe, professional and amateur astronomers contributing data, multiple wavelengths and techniques brought to bear on characterizing 3I Atlas as thoroughly as possible. The campaign has specific objectives. Measure the light curve continuously to detect any variations in brightness that might indicate rotation, outgassing fluctuations, or structural changes. Obtain spectroscopy across visible, infrared, and radio wavelengths to identify chemical composition and physical state. Track position precisely to refine orbital parameters and detect any ongoing non-gravitational forces. Image the comet at the highest resolution possible to resolve spatial structure in the nucleus and coma if present. Some of these observations require clear skies, dark sites, perfect weather. Clouds block optical telescopes. Atmospheric turbulence degrades image quality. Observatories will compete for precious hours of optimal conditions. But the campaign is distributed globally, so clouds over one continent mean opportunities for another. The network approach ensures continuous coverage. Space-based telescopes have advantages. Hubble will perform ultraviolet spectroscopy in November, looking for specific emission lines that reveal the gas composition and the sulfur to oxygen ratio, which says something about where the comet formed and what conditions were like there. Webb is scheduled to observe again in December after perihelion, using its infrared instruments to peer through any dust and measure thermal emission from the nucleus. The ESA's JUICE spacecraft, currently en route to Jupiter, will be positioned to observe 3I Atlas in early November. JUICE has limited imaging capability, but might detect gross features like a dense gas cloud if one exists. Ground-based radio telescopes will look for molecular emission lines characteristic of cometary outgassing, water, carbon monoxide, hydrogen cyanide, methanol, others. All this data will flow into a central repository where researchers can access it for analysis. The Minor Planets Center coordinates the effort, collecting observations and producing refined orbital solutions. Papers will be written, results will be debated, models will be adjusted to fit whatever we learn. This is science in action. the slow, careful accumulation of evidence that eventually resolves uncertainty. But the key date remains December 19th. Closest approach to Earth means optimal geometry for observation. Hundreds of telescopes will point at the same target simultaneously. If there is a massive gas cloud around 3I Atlas, we will see it then without ambiguity. If there is not, we will know that too. What happens after December depends on what we find. If the natural explanation holds up, 3E80 Atlas becomes a fascinating but understood object. We will continue observing it as it leaves the inner solar system, tracking its trajectory past Jupiter and beyond, gathering data about its composition and structure until it becomes too faint to detect. It will join Oumuamua and Borisov in the small catalogue of confirmed interstellar visitors, valuable for what it teaches us about how other planetary systems form and evolve. If the natural explanation fails, if we cannot reconcile observations with known cometary processes, then 3I Atlas becomes something else, an anomaly, a mystery, potentially the most important discovery in human history. The response would escalate. More resources would be allocated. Attempts might be made to send a mission to intercept or at least make a close flyby of the object before it leaves. Communications would be attempted, though what message you send to an object that shows no signs of reception capability is unclear. The broader implications would unfold over years. Confirmation that we are not alone would fundamentally alter humanity's view of itself and its place in the cosmos. The technological implications of interstellar travel, if that is what we are witnessing, would drive research in propulsion, energy generation, materials science. The sociological implications of knowing other intelligences exist would reshape philosophy, religion, politics, culture. But we are not there yet. We are in November, watching a comet emerge from behind the sun, waiting for instruments to gather light and turn it into data. The universe does not care about our expectations or our speculation. It simply is what it is. Our job is to look carefully and honestly at what the evidence shows, then draw conclusions appropriate to that evidence. 2 weeks until the test. 2 weeks until we know if this story ends with interesting comet or begins with everything changes. 2 weeks. Let me bring you back to where we started. An object from another star system accelerated in ways that gravity alone does not explain. The acceleration occurred at perihelion during a window when direct observation was difficult. The object displayed a blue color when it should have appeared red. It is orders of magnitude more massive than statistical models say it should be given our limited sample of interstellar visitors. Its trajectory aligns roughly with the plane where planets orbit, taking it past multiple worlds in our solar system. Each of these facts has possible natural explanations. Together, they form a pattern that refuses to resolve into comfortable certainty. Maybe that is okay. Maybe uncertainty is the appropriate state when observing something genuinely new, something that does not fit neatly into existing categories. Science advances by confronting the unknown, not by forcing premature conclusions. What we know for certain is limited. We know 3I Atlas exists. We know it came from interstellar space. We know it displays characteristics of a comet, but also shows behaviors that puzzle comet experts. We know it is currently moving away from the Sun on a trajectory that will take it past Earth in December and Jupiter in early 2026, before leaving the solar system permanently. What we do not know is more extensive. We do not know exactly where it came from, what stellar system it originated in, how long it has been traveling through the galaxy. We do not know its precise size or mass or composition, though observations constrain these parameters to reasonable ranges. We do not know whether the non-gravitational acceleration resulted from natural outgassing or from some other mechanism. We do not know what December observations will reveal. The scientific process will continue regardless. Telescopes will gather data. Researchers will analyze results. Papers will be published. Hypotheses will be tested. Slowly, methodically, the uncertainty will narrow. Most likely, 3I Atlas will turn out to be a natural but unusual interstellar comet, teaching us things about planetary system debris and ice sublimation in exotic conditions. The anomalies will resolve, the mystery will fade, but there remains a small possibility, a probability that most scientists would place below 1%, but not at absolute zero, that 3I Atlas represents something fundamentally different. That possibility is worth taking seriously, not because it is likely, but because the implications would be so profound. If we are wrong and dismiss it prematurely, we miss perhaps the most important discovery humanity could make. If we are right and pursue it appropriately, we verify what most expect and move on. The December observations are designed to discriminate between these possibilities. If we see the predicted gas cloud, natural explanation confirmed. If we do not, questions escalate. The test is binary, the result will be clear, and then we will know which direction this story goes. For now, 3I Atlas remains what it has been since discovery, an interstellar visitor that challenges our understanding and demands our attention. A comet that might be just a comet, or might be something that changes everything we thought we knew about our place in the universe. The next chapter in this story is being written by photons crossing the void, by data accumulating in computers, by humans asking questions and seeking answers. By December, we will have those answers. Until then, we watch and wonder and wait to see what the universe has decided to show us. Because 3I Atlas is still out there, moving through space at speeds that mock our fastest spacecraft, carrying whatever secrets it holds toward its closest approach to Earth. And on December 19th, when the geometry aligns and the telescopes focus and the data streams in, we will learn whether this story ends with a period or opens with a question mark that echoes across all of human history. The comet does not care which. It simply continues its trajectory, indifferent to our theories and hopes and fears. A messenger from the cosmos, carrying information we are only beginning to decode.